Okay, so hi everyone. I am Anton from Elias Audio and Elemental Games. And I'm going to be talking a bit about real-time ray-traced acoustics, and specifically how we do that using impulse response synthesis directly in the game engine from geometry, and use those impulse responses to apply the acoustics in real time using time-varying convolution in our spatial audio pipeline. So I will start with a brief introduction to game audio acoustics, and then explain this particular approach, and then end with how it functions in action. So in acoustics, the impulse response is a signal that encodes exactly how sound is propagated from a source to the listener. So you can imagine an impulse being created at the source position to the left there, and then you would have sound bounce around in the room, and then if you recorded the response of that at the listener position to the right, you would get something like this. Typically, it would start with a direct sound tap in the very beginning, followed by a couple of distinct early reflections, and then it would end in a more diffuse late reverberation tail. And the cool thing here is that if you have the impulse response, you can reconstruct the acoustics of that space. And the way you do that is by applying the impulse response to audio using convolution. So just a quick note on acoustics and game audio. It can be, there's a sea of methods and effects that you can see in games, but usually they are grouped into direct effects like occlusion, and then indirect based on reflections and things like that, that you can group into reverbs, which is the type of effects that I will be focusing on in this talk. So still in games, we mostly see fairly static approaches, where you maybe have a couple of pre-authored impulse responses defined across the game geometry using reverb zones or grids, and then depending on the listener position, you pick an impulse response or interpolate between a couple of them, and then you feed that into a convolution reverb to apply the reverb effect. And while that can sound really good, it's a pretty static approach that doesn't really change over time as the listener moves or the environment changes. So on the other end, we have more dynamic approaches that actually use the game geometry and then raycasts on that geometry, or use image source methods to extract spatial information. And that is then used to drive algorithmic reverbs and delay lines. To simplify a bit, traditionally there's been sort of a trade-off here. You could use like a combination of these two, and there are some solutions that try to bridge these two, but yeah, traditionally there's been sort of a trade-off. And so in this approach, we try to bridge that gap and sort of get the best of both worlds. And the way we do that is we at runtime do two things. So we generate the acoustics by synthesizing a listener-centric impulse response using ray tracing in the game engine. And then we render the acoustics using the impulse responses in a time-varying convolution filter. And I should say that that's maybe easier said than done, But yeah, let's dive into how we do that. So the system on a high level is split between the GPU and the CPU. So we use the GPU to ray trace the geometry and synthesize the impulse response. And then we use that impulse response on the CPU to render the acoustics. So these two parts are run continuously in parallel. And the transfer between them is asynchronous and completely weight-free, so we don't block the audio thread. So let's zoom in a bit on what we actually do on the GPU side. So the work on the GPU is structured as a sequence of shader passes. So first we ray trace the scene to build up an impulse response. And then we post-process that impulse response to shape it to what we want it to sound like. And then we prepare it for real-time convolution by transforming it into the frequency domain with the fast Fourier transform. So in the ray tracing pass, we use a geometric model of sound wave propagation. And we start by casting a bunch of rays uniformly in all directions from the listener. And we let them bounce around in the environment. And as those rays hit surfaces, we accumulate their reflections into what will become the full impulse response. So specifically for each reflection, we try to estimate how much of the reflected energy actually returns back to the listener. So we compute the amplitude based on material properties and the path length of the ray. And then we encode the direction of arrival in ambisonics. So we get a spatial impulse response. And then we add that contribution to the impulse response at the computed delay. So if you would use the impulse response that you got directly from the ray tracing, it might not sound that good because you will always have a very limited ray count. Even if we shoot hundreds of thousands of rays, it would still be a pretty sparse late tail in the impulse response. And even if the impulse response turned out to be dense enough, we would prefer to have full control so that we can actually use this as a creative sound design tool and not just being a rigid physical simulation. So what we do is that we run the ray-traced impulse response through a post-processing pipeline. So yeah, to summarize, we run it through first a diffusion pass, which sort of lets you extend the reverberation time if you want. And then we smear the impulse response to control the density and the texture. And then finally, we run it through an EQ and a limiter to control the timbre and the dynamics of the impulse response. And as a final GPU shader pass, we prepare the impulse response for real-time convolution. And to do real-time convolution, you have to partition the impulse response. So the way we do that is by first sectioning it into an early region and a late region, where the early region covers the early reflections and has as small blocks as possible to minimize latency. And then the late region covers more of the late diffuse tail and uses larger blocks, which is more efficient. And then each block gets transformed into the frequency domain using the FFT. And this is perfect to do as a last step on the GPU because, well, you can run all these different blocks in parallel on their own GPU threads. Okay, so on the CPU side, we use that impulse response produced by the GPU to apply the acoustics in a convolution reverb. So the thing is that if you would just use the impulse response or swap the impulse response as audio is playing, you would get audible discontinuities. So you need to do smooth transitions somehow to get time varying convolution that sounds good. So we triple buffer the impulse responses. So we have a queue of at most 3 impulse responses at a given moment. And then the convolution itself is a non-uniform partition convolution that also operates at a lower sample rate, and we stagger the late blocks to evenly distribute the CPU load. But that's just the convolution part. So the way we make it time varying is that during an impulse response update, we do different crossfade strategies in the different regions. So for the early blocks, we use a basic time domain crossfade, but we're able to use in the late blocks a crossfade directly in the frequency domain, which is a lot more efficient. So this is the early block transitions, just a regular windowed crossfade. Nothing fancy there. But in the late blocks, since they are longer than the early reflection blocks, we could actually do a crossfade that is long enough that wouldn't sound sort of like a discontinuity in just one block. And that enables us to do the crossfade directly in the frequency domain using what's shown here in the diagram. So it's pretty much just using the Fourier transform of a cosine window. And that lets us do a single inverse FFT, which saves us a lot of CPU. Okay, so what does this look like from an authoring and sound design perspective? So instead of having to draw reverb zones or hand author impulse responses in advance, the idea is that you would tweak the acoustics using material properties, things like frequency-dependent absorption and scattering parameters. And you can also tweak these impulse response post-processing parameters to make the reverb sound the way you want. It doesn't even have to be like a realistic sound. You can go nuts and make all sorts of stylized soundscapes with it. So the idea is that you would focus more on character and not so much on placement of the effects. So to give you an idea where this lands in practice, we're currently targeting under 1 millisecond on the GPU per game frame, and then under 2 milliseconds on the CPU per audio callback. And on our test setup, these are the numbers that we currently use that hit these targets. So we shoot in the order of a couple of 100,000 rays in the ray tracing pass and let those rays bounce up to 8 times, which gives us a fairly detailed impulse response. And that is amortized across 4 frames, which gives a reasonable update latency. And then we were able to use 8-second long impulse responses, which is definitely enough to capture the largest and most reverberant spaces in the game we're working on. So that's what the points look like, at least. So you can sort of maybe internalize how that impulse response what that would sound like. But that's 8 seconds long, and you see the time domain representation and the blue plots there, and then you have a spectrogram underneath that. And the cool thing is that all this is rendered dynamically and updates in real time. But anyway, the conclusions here is that using this hybrid GPU-CPU architecture, real-time ray-traced acoustics is actually kind of feasible and practical. We're already using this approach in the development of Elemental Games' upcoming debut title. So to summarize, we do impulse response synthesis using ray tracing, so we don't have to use any pre-baked data. Then we do GPU accelerated post-processing to shape the impulse response. Then we do non-uniform partitioned convolution and a hybrid time frequency crossfading to get seamless transitions. And in the end, this gives us a dynamic acoustics pipeline that runs in real time. Right? Thank you.